well, whatever degrees it is. Okay, so there was a problem like this one, a little bit, kind of, but where you're pushing on an object, pushing or pulling. But if we look at all the forces on here, on this object, we have the mass, we have the F of n is what? Normal force. And since we're on a horizontal surface, it is equal to the weight. They're equal to each other. We're pulling, or we could have a pushing force. We have x, and then we split it into components, f of x, f of y. And so that would be our force diagram. We're using all of the same equations basically. I just put in some specifics like the force applied. I made it force pull. You can make it force applied, doesn't matter. But we're just basically going to be using our trig functions. Force of the pull in the y direction. Yeah. Yep. Okay, then we look at the net forces in the y direction when we look at that picture. Our y directional forces, we have normal forces up, and we're going to add the y force here, and then we'll subtract the weight. So that's what this is. We have the normal force, we subtract the weight, which is mg, add f of y, and if we're not accelerating in that direction, it's going to equal 0. Usually we're not accelerating in the vertical direction, so that will always equal 0. The normal force, I misspoke before. The normal force, since we're not pulling horizontal to the ground, it's not equal to the weight. It's equal to the weight minus normal or the y force. Normal force is kind of like the apparent weight, just like when we were in the problems we did with the elevator. When we went down, we felt like we were lighter. If you're pulling up at a certain angle, it's actually going to make that box or whatever feel a little lighter, kind of apparent weight. That's the normal force. And then the x forces, all we have is the f of x and the x direction, and that is equal to ma. And I put max just because we're accelerating the x direction, so you can keep that straight. So if we want to do a problem like this, James exerts a force of 72 newtons along the handle of a lawnmower to push it across the lawn. Find the horizontal component of the force when the handle is at an angle with the lawn of 60 degrees. Basically, kind of like what we were doing yesterday. Well, that's not very straight. So if we're pushing a lawnmower, we're pushing, so we're going down at this angle. This angle is 60. And this is 72 newtons. Yeah. It'd be like you're pushing down and the handle is, yeah. At same angle, yeah. So we would use, if we're going to find f of x, should have made a new page. Adjacent over hypotenuse is equal to cosine of 60, right? So 72 times the cosine of 60. So f of x is equal to 36 newtons. Then if we knew the mass of the lawnmower, we could find the acceleration of the lawnmower. It'd be 36 is equal to ma. If we wanted to find that. I don't know, maybe that's what the next problem does. I don't remember. And we'll talk about friction. We won't do all the problems for it. We'll finish some of the problems up on Monday. So here, same exact situation, but we're going to add friction in. And just remember that friction is opposite the direction of movement. So since f of x, it's going to be opposite f of x. Since f of x is to the right, friction is to the left. So they're always going to be opposite each other. Otherwise, everything else stays the same. And our f of y equations are going to stay the same. The f of x is just going to change because we're going to have f of x. The sum of the forces in the x direction is to be f of x minus f of f equals max. That's the only thing that's really going to change. Okay. Now sometimes if you're like pushing x, or pushing down, x will be to the left, so then friction will be to the right. It shouldn't really matter that way. They're just opposite. So let's do at least one of these. Oh, let me go back. So 95 kilogram chair is being pulled along a carpeted floor at a constant velocity. Constant velocity, what does that tell you? And are we accelerating? No, so acceleration is 0 since we're going to accelerate a constant velocity. The frictional force is 53 newtons. What's the pulling force if it's being applied at 44.8 degrees to the floor? Whoops. Ah, yes. F of x is equal to the frictional force. We'll draw a picture to show that. Okay, how big is our chair? 92 kilograms, is that? 95. And it's being pushed, correct, or is it pulled? Pulled. And what's the angle? And we know friction is equal to 0.83. The force of friction was that small? Oh. Wait, I think, just a second. I think what I have on my, change it, oh shoot. Change it so it looks like what mine, I think I remember this. Change it so it looks like mine. 95 kilogram chair, it tells you the frictional force is 53 newtons. And then the angle. Coefficient of friction, remember, is mu, so if we ever do see that. Yeah, we'll do several of those. So we have 53 newtons here. So, but our acceleration is 0 since we're going at a constant velocity. So our f of x, our force, because it's asking for f of x, right? Or what does it ask for? Oh, what's the normal force? No, what's the pulling force? So it's looking for this right here. Yes. So we can find f of x, because we know f of x minus f of f is equal to max, correct? Yeah. This is 0, though, because acceleration is 0. So that means that our f of x is equal to f of f. And that is equal to, then, 53 newtons. Yeah, I changed that, so that should be 53 newtons for friction. 53. Okay. So we have 53 divided by the cosine of 44.8. $74.7. There we go. Look and see. Right. And then I added this other, what's f of n? Well, you would just use this. So we have the sum of the forces in the y direction is equal to, we have the normal force minus the weight plus f of y. And that equals 0. So what's our weight? 95 times 9.8? 931. So 931 minus Fy is 52.6. So we get then 878.4. That's newtons. And now, just for kicks and giggles, what would mu equal then? Because f of f is equal to mu times the normal force. That's our equation for friction right here. Erase this. And so 0.06. We take 53. 53. Yep. There you go. So on the board over there, there's a little assignment, the page 865, 1, 2, 5, 6, 7, 7, or 10, 11. Work on that. We'll finish the problems on the friction on Monday, and then those problems we do at the end of the period on Monday. So I don't know how much time we'll have. How many problems are there actually left that we would have to do? Oh, there's only one more. So maybe we'll do friction and equilibrium. Do a few notes, and then the problems we do at the end of the period. Or if